Welcome to this video looking at charged particles in magnetic fields, part of the particles and waves topic for higher physics. What are we looking at? Well, we're looking at what happens to charges when they are in a magnetic field and a way to determine the direction of the force on these charges, knowing the details about the magnetic field and how the charge is moving. So our knowledge of motors may tell us that we know that when a current flows through a wire, we get a magnetic field produced. The direction of the magnetic field around that wire depends upon which way the current flow is. Magnetic fields, remember, have a north and a south. And we can look at that with something called the left-hand grip rule. So if you take your left hand and you wrap your fingers around just how they would normally go, then you've got a circular field around this wire and the direction is moving in a clockwise direction if the flow of current is going upwards. If the flow of current is going down the page, then the direction of the field is circular again, but it's in an anti-clockwise direction. Okay, this is not important to know, but it's of help for what we will come to later on. So if we have a wire carrying an electric current, it will experience a force when we put it at an angle to a magnetic field. And this is the effect of motors. In a motor, we've got a current carrying wire within a magnetic field and we get some movement. We can use the right-hand motor rule to show the way this movement is. So you need to be practiced at this. There are a number of ways of looking at this. So we'll look at this. We'll also look at one you can do with your left hand, and it's up to you to pick the one that you're going to choose. So if you point your fingers, and what you've got is you're going to have them looking at all different directions. So if you make your hand the same shape as the diagram there, your thumb is pointing upwards in the Y direction, let's say. Your first finger represents the field in the X direction, and then 90 degrees to both of those is your second finger, indicating the direction of the negative charges. Okay, so we can use this. If we have positive charges, we can use the opposite hand, or we can work out what would happen and change it around. But let's have a look at what we might mean. There's a similar thing that you can do, looking at the palm of your hand here, with the thumb for particle motion, the palm for the force, the fingers for the magnetic field. Personally, I prefer the right hand one, but this one works too, as long as you get the labels correct and the right or left hand also correct. So let's have a look at this one here. So how do we represent X, Y, and Z on a flat screen or piece of paper? Well, we can do this with crosses and dots. So the crosses here indicate that we've got a magnetic field that is going directly into the page. It's like you're firing an arrow, and the end of the arrow would be where the feathers are, or a dart, and the end of the dart would be where the flight is on the dart, and you would see that cross bit going away from you. So the crosses here are representing the magnetic field that is going into the page. If the magnetic field was coming towards you out of the page, it would be represented by a dot. So here we have a negative charge, and we have to work out which way is the force. So we're going to take our hand here and we're going to put our fingers out. So we've got our thumb, right hand, thumb pointing upwards, first finger pointing towards the screen at the moment. We can change it in a minute. And our second finger pointing to the left. So they're all at 90 degrees to each other, like the diagram we showed earlier. And then we're having a look. So the first finger was the field. So the field is pointing into the screen. Second finger is the direction of the negative charge. So that second finger needs to point to the right because the negative charge on this diagram has an arrow showing it's got velocity v moving from left to right. So you're going to have to turn your hand upside down, your right hand upside down, and your first finger is pointing towards the screen. Your second finger is pointing to the right, and your thumb is now pointing downwards. And that's the direction of the force that you get. And we would need that force because if it's going to follow that curved path that we can see there, how do you get that? Well, you get that by a force that is downwards initially. Okay, so the first finger field on your right hand into the page because the cross is showing it goes into the page. Second finger, direction of negative charge to the right, turn your hand upside down, your thumb is downwards. So that's the way of the force. Okay, let's have another look here. So first finger is the field. The field is going downwards. So you need to put down the screen, down the page for your first finger. Second finger, direction of negative charge. The negative charge is going from left to right. Your finger, if you just picked up your right hand, is pointing to the left. The big arrow showing is not, so the force is the thumb. So your thumb is going to point to the right here. So if your thumb is pointing to the right, the direction of the force, your first finger is pointing down the page, the direction of the field. Your second finger there, the direction of the charges moving is into the page, into the screen. Let's have a look at another one. Okay, so another negative charge that is moving, this time left to right, rather than the force. And we have the field lines. Now here, if we try and point our fingers, we're saying, well, the field is going to the right, so I'm pointing my first finger that way, and then I'm saying I can't point my second finger, the direction of movement of negative charges, in the same direction. So there will be no effect in this case because it's moving parallel to the field. The movement has to be at right angles or at an angle to the field for there to be a force. So in this case, nothing is going to happen. There's no force. That's in the same way that if you consider a horizontal projectile, it doesn't accelerate horizontally, it only accelerates vertically. Let's have a look at this one then. So first finger field on our right hand, which way is that going? The cross. So the arrow is going away from us into the page. Second finger, direction of negative charge, down the page because it's an electron. So it has negative charge. Which way is your thumb pointing? Well, it should be pointing to the left if you're using your right hand here. Let's have a look at this one. First finger field, again into the page. Second finger, direction of negative charge. This time we got a proton. What do we know about a proton? Proton has a positive charge. So we can either use our other hand, our left one, or we can point our second finger in the opposite direction. So I'm going to point my second finger not the way the arrow of the proton's going, but to the right, which then makes my force go down. Or I can use my left hand, first finger field still, second finger for my left hand, the direction of the positive charge to the left, and my thumb is pointing down. So the force will be down for this one. And finally, let's have a look at this one. So now we've got dots for the magnetic field. So the dots are indicating that the magnetic field is coming out of the page towards you. So if you take your first finger and you point it towards you, It's a bit sore because turning it around is not that straightforward. And then we're saying, right, well, for this to go in a circle, there must be a force that is acting to the right here, because that's how we get it from going there to going that way later on. There's a force towards the center of the circle. So the field is coming towards us. The force, starting with where our particle there is, going from left to right, and our finger is going down for our right hand, and so that is telling us that this one here is a negative particle. If it was a positive particle, what would happen is that we would, if it had the same mass, it would still move in a circle that would have the same radius, but it would be moving in the opposite direction. Now, of course, it would have to be within the magnetic field all the time, so there would need to be the field lines over here as well. So the difference between the particles is that if you have a negative particle, it will rotate in one direction. If you have a positive particle in a uniform magnetic field, it will rotate in the opposite direction. There can also be differences depending on the mass. If it's a smaller mass, it will be a smaller circle than if there's a larger mass.